Yeah, we have gone live.
And it's given a few minutes, I think. Folks are trickling in. Let's give it a few more minutes and we'll kick it off. All right, let's go. Hey everyone, welcome to a battle of costs and scale at RootConf. This talk is brought to you by RootConf. Honestly, we started this as a part of the Cloud Cost Conference. But when Lokesh and Rohit's talks came in and we started looking at the proposal in deep, we figured the talk stood on their own. And so here we are today. We have a bunch of folks on Zoom. There are a few people coming on YouTube, or perhaps you're watching this at a future date through a recording, but you're welcome anyway. Today is about infrastructure optimizations, and it's also a war story. So I'll let the speakers go in depth about the material, but basically both of them were part of a team that underwent a large period of time where they had to optimize their costs, practically staring down like existential crisis. Right, the whole industry was trying to get their costs in order, and Team Udaan was no different. And so both our speakers, Lokesh and Rohit, went through that journey. And what they're going to talk about today is what problems they faced, what approach they took to solve the problems, what came out of them, some conclusions, some lessons, and things around it. Right? It's what you call an experience report. And we also have a panelist with us today, Sarika. Sarika Atri brings years of experience on this particular topic, engineering infrastructure. She has worked with marquee names like Flipkart and Hotstar. And she's also been involved with reviewing talks for the Cloud Cost Conference. She's helping RootConf out. A quick word about RootConf. This whole conference is possible by member subscriptions. There are more things lined up. There are different talks, different types of conferences. If you want to geek out on things like infrastructure, SRE, metrics, logging, RootConf is the place to be. And RootConf as a part of the Hasgeek umbrella, and Hasgeek has other things like data policy, security, engineering culture, all of those things. And so this whole series of talks is a curated offering along those lines, right? So without further ado, let's jump into the talks. First up, we have Lokesh. In his own words, he's a builder at heart. and a software engineer at Udaan, and he loves databases, tech, and dancing. So I guess today there's going to be no dancing, but there will be databases and there will be tech, right? So I'll let Lokesh take over.
Thanks, Swanan. Cool. I'll just share my screen. Cool. So I hope you guys are doing fantastic. Hoping you guys don't have deployed anything to production before joining the session, and no nightmares are waiting for you. Cool. So over the last 2 years, we've had a crazy ride with SQL Server, dealing with scale month over month, while on the constant quest to improve our cloud economics. Today, I'm tasked with summarizing this entire journey in 25 minutes or so. So, okay. So just to get you guys excited, this is the trend line that we have quarter over quarter of our SQL Cloud Infra bill. This is normalized to 100. But you can see like we've had a lot of shifts, sharp drops, where we took major decisions for dropping our cost. And if you're one of the math geeks, essentially the area in blue is sort of if you sort of calculate the area of it using the principles of integral calculus, that turns out to be the cost that we actually incurred. And the unshaded area is essentially the cost that we would have incurred if we hadn't reduced our cost. So it's a huge area that we saved up eventually. This is a long journey of around 2 years. But yeah, I'll jump into every bit of it. Okay, so I think Swanan already introduced me quite well, so I'll just jump into the agenda right away. So we'll be talking about the background of how we started, what Udaan is, and then we'll talk about certain strategies of optimizing databases. What is how do you choose the right offering? How do you choose the right indexes? What are the query gotchas you need to be aware of? Database operations, maintenance, and building tools to make your life easier. Yeah, that will be it. Cool. So I'll just set the background and context of how Udaan actually came into picture. So India is a $1 trillion plus distribution industry where it's highly unorganized and fragmented, with like 20 to 30 million merchants. And so Udaan came about in 2016, where we tried to solve a lot of problems in digital financial supply chain and the commerce space to make sure the merchants and traders and businesses, all of them have an easier life. So this is Udaan in glance. We have 3 million plus retailers, kirana shops, chemists, farmers, and 500,000 products across 2.5 million brands. We do more than 5 million transactions every month, handling over 2,000 or 7,000 tons of food products on a daily basis. That makes us the largest grocery player in the country. We have spanned over 1,200 cities and over 12,000 pin codes across India. So Udaan is not just catered to the commerce part of it, but making sure the entire life cycle of it, which includes the credit lending part, which includes the payments part, which includes warehousing, hubs, supply chain, fulfillment, and pretty much every bit brand awareness, ads, every bit that involves merchants and traders, we sort of try to make the life of our customers easier. Jumping into the tech part, Udaan has an interesting RDBMS landscape. We have over 100 databases that includes all dev, stage, and prod. And we house over 250 services and hundreds of cron jobs. Now, for the cloud provider of choice was SQL Server for us. Azure was for us. And we primarily use Azure SQL Server and all offering of it, essentially in a good mix. While we have certain Postgres instances as well, but majority of our SQL workloads are on Azure SQL Server. So for the majority of the talk, I'll be focusing on Azure SQL Server, but the learnings apply pretty much to all other relational databases, and in fact applies to all databases for certain tips. Cool. So just to summarize, what is it that we did at Udaan? Essentially, over the last 2 years, our GMV kept going up, while our business breadth was going up as well, like increase in the number of verticals, products, capabilities, features, warehouses, pin codes. All of this was going up. We were constantly iterating on our business network design. At the same time, we were trending downwards in our infra cost. And this is not per unit cost, this is total cost. And by the way, this is not a correlation. This is a deliberate effort and the focus that we put into this area to make sure that happens. Once again, looking at the cost trend, we've been going down month over month, quarter over quarter. And the interesting thing that I want to sort of highlight in this talk is that no matter how you think the database is running efficiently, there are always avenues and levers that you can look into and weigh in the right trade-offs, understanding your business, and then take calls accordingly to give you to reach a more efficient state in your database. So yeah, the question remains: how do you do that? How did we reduce our 80% of database cost while our business was growing exponentially? Before that, let's talk about certain key elements for it. Like, who should care about database efficiency? Is it the product engineer who is building, who understands the business context, design of the system, writes the code? Or is it the database administrator who understands databases inside out? So there is always this gap between these two sort of parties. While product engineer does not have the bandwidth or the expertise to always take care of databases, because they are tasked with thinking about things, metrics like what is my user retention looking like, what is my conversion looking like. So they always don't have the bandwidth or sometimes expertise. But the DB understands the depth of the database, tuning the database, but they often lack the context to take the right decisions. So this gap can be sort of bridged by if someone has the entire picture. This is the kind of philosophy that we run with, that if product engineers have the right tools and right understanding of things, they can take the decisions in a more fruitful way, in a more thought through way, taking into the business vision into context. Yeah, so that's the philosophy here. But yeah, going into the actual strategies, I'll be talking about all the learnings that we had from the journey. And I have compiled over 18 practical no BS tips that we implemented. So number one is, I have 3 buckets where I categorize those tips. One is, how do you choose the right offering? Then how do you choose the right indexes, and how do you work your way around certain query gotchas, and sometimes the SQL query plan does not favor you at all, and how do you deal with all those things? And how do you actually take care of your database, because database needs care too. How do you leverage the right tools to make sure your database is running optimally, not just on the day one, but on the day end? So yeah, let's jump into the topic number 1, which is choosing the right offering. Now, we have tried a lot of offerings within Azure SQL, and we have tried a lot of options, and we have compiled a lot of learnings from using all the options. So number 1 is you don't always need the local disk. Now, what is local disk? Is essentially when your compute and storage is co-located in a single machine. This is obviously a faster approach where you have lower latency because you're accessing the disk right away. But that's often costly. It's often Now, one more disadvantage is that every time you need to downscale or upscale, you need to spend extra hours. Now, remote disk, on the other hand, is in most cases not the default, but is something that worked out for us for a lot of business use cases. We didn't need that high of a we didn't need that much higher IOPS. We were okay with high latencies, slightly higher latencies, I'd say. So we took this call, and we had zero impact on the business, but we ended up saving a lot of money. So yeah, key learning is you don't always need it. And there are a lot of tiers which include it in the finer details. But yeah, if now that you know that this is something to take care of, I think you'll have you can take a better call on this. Second is leveraging elastic pools. Now, if you remember physics, there was a topic called wave superposition. Essentially, what happens is when you have multiple compute utilization patterns, and you think they are fitting right into each other, giving you a very constant graph. For example, you have a database that is active at night, but not so active on the day. And you have another database which is active at day, but not so active at night. What do? You place them in a single machine, in a single elastic pool. So yeah, they are essentially complementing each other. So you don't have to pay for the machines twice. You can just use the same machine. So this is a strategy that we used. Again, now, if you understand the product and workload patterns, you can effectively take calls on this. Third tip that I have is exploiting serverless databases for variable workloads. Now, I think recently there's been a lot of talks about stories of serverless going bad and how switching to monoliths sometimes giving the best results. And that is something that we experienced too. But in a lot of cases, we saw a lot of flexibility offered by serverless that worked best for great cases. So like you can see, there is a spiky behavior. So you don't have to provision for the maximum capacity. The database can upscale and downscale by itself. And in certain cases, we saved money by switching from serverless to provision, because if I know the right patterns, then I don't have to pay for the base higher price, which is close to 1.5x. Yeah, that is one. Yeah, this is a very interesting learning that we had, that certain decisions in your design journey are irreversible. Sometimes, so I'll give you an example. So there is a database which has use space of 3.2 terabytes. Can I migrate this to a 4 terabyte machine? I mean, if you had asked me 2 years back, I would have said yes. Why not? But then we had an interesting learning that there's something called allocated space. Like if you've used Windows in the past, there is something called disk fragmentation, disk defragmentation. So your data is spread over a 5 terabyte space. You can't transfer it to a 4 terabyte machine. You need to shrink it. You need to, I don't know, defragment it. So this is something that haunted us quite a lot. We expanded from a 4 terabyte to a 5 terabyte machine. This was a one-click thing. But then reducing it back to 4 terabyte was so painful. And that also takes into account the cloud economics, where sometimes the cost increase is not linear. So this 5 terabyte database was not 25% expensive. It was 4x more expensive because it required special machines. So we had to design a raw comprehensive migration strategy that took us, I don't know, months to figure it out. But then we saved more than 70% in cost just by this single operation. Yeah, I think, okay, this is not meant to be a pun. This is a very serious tip that you always should negotiate with the cloud provider. Despite of whether you think you can achieve a lot in tech, you can achieve a lot with negotiation alone. So don't be that guy. Talk to your IT team, contracts, legal team, I don't know. But yeah, make sure you initiate this conversation. Okay, so let's jump into topic number 2, which is how to do the indexing the right way. Now we've had a lot of learnings from, or rather assumptions that we had about how a query works, but some of the things backfired, and then now we have learnings to talk about. One of the learning that I have is when you talk about varchar and varchar, it sort of sounds like, it seems they're the same, right? Okay, there is a size difference in the data types, but the major learning that we had was it cannot be used interchangeably. So when you have a column which is varchar indexed, if you query it with an varchar, your data will scream at you. It will convert it for you, but your query cost will spike up. So there's this crazy diagram that I'm showing you. This is the matrix of what data types and what data types can be implicitly converted. While SQL is doing a great job as doing those things for you, but then the cost of conversion is high. So you should always make sure that it doesn't convert. So the nightmare that we had was the JDBI always converts string to nvarchar instead of varchar. So the columns that were varchar were implicitly converting. So just by looking at all the varchar columns and converting it to nvarchar, we saved 20% in CPU spike. Like easy gains. Also, you should be beware of key lookups. So sometimes query plan like this looks okay, right? When you look up an index, it doesn't contain all the data, so it looks back to the original table. But then when the query volume is quite high, this key lookup is something that you want to avoid. So what you can do is you can probably create certain special indexes to bring it down to a very simple plan like this. Don't worry if you don't understand this entire concept. The key to understand is that you can always create an index that answers the query, everything within it. But then if you overdo it, you have write application problems. So I've come up with a very simple decision tree of how do you think about it. If the query cost is high and there is a lot of write volume, you probably don't, and there is a lot of query volume, but write volume is less. You probably create an index, and that makes sure that you avoid that lookups. Okay, moving on. This is a very tricky tip that we encountered was we all know that indexes are ordered in nature. They are prefix ordered. But this one is interesting because the specificity of each column filter matters a lot. So if a column, the first column is giving you a lot of filtering criteria, that means you should pick that column first. So you want to filter out as many of those in the first pass and then the second pass. That is the ideal way to go about it. And you'll see a lot of performance gains just by doing that. Okay, compression. I think this is a problem that can be applied in a lot of software engineering areas. But the idea is we saved up close to 40% in database storage just by compressing. There are a lot of ways of compression, like row compression. There's regular compression and there's page compression, and they use different strategies like row, prefix, and dictionary compression techniques. But then you need to make sure that you do it only for tables or indexes rather, which have very low update ratio. And there is a handy query to compute update ratio. You can just Google it. But yeah, if the update ratio is less than 10%, then you are probably in the good area to compress the indexes. How does it work is that you store the database pages in a fewer number of pages now. And if my assumption is correct that IO is lesser than the CPU cost, then I end up saving a lot of latency, right? And a lot of IO, obviously, but maybe at the cost of CPU. So that's a trade-off that you need to make. Yeah. One more thing that is very specific to SQL Server is that SQL Server does not have a GIN index. So how do you create an index on a key which is inside the JSON? Very interesting. You can just create a computed column and you create an index on top of that. So easily we were able to convert a clustered index scan to an index seek at the cost of one index, right? Yeah, that is something that we have used quite a lot. Okay, this should be common sense, but this is something that we sort of were not doing that well enough. Is something we were overloading the master. No matter what kind of workload it is, we were hitting the master because we were sure that it contains the latest data. Learning was we don't always need the latest data, especially in case of cron jobs or some analytics tasks. So we can offload some of the workloads to secondary. And better yet, if you have a data warehouse or data platform for that matter, which is constantly syncing periodically with your base data tables, you can always offload some of the read workloads to those while your primary is taking care of all the writes. Okay, so let's jump into the pampering part of the indexes and database. Like, how should you take care of the database? And obviously, we built a lot of tools along the journey because we figured out we need those tools, and there are no alternatives out there. So we built a couple of tools. We'll be talking about that. First one is let's talk about redundant indexes. It's one of the areas that I love. Okay, let's warm up first. Let's have index 1, index 2, both have the same columns. How should we get rid of redundant indexes? Easy, right? You just delete one of them. What if this is the case? A, B, C, and A, B. As we know, indexes are prefix based, so you can delete the index which is A, B, right? Easy enough. Let's take a bit notch higher. What about if the indexes have the same columns, but they are in reverse order? Now, this is interesting, right? You can't directly delete because indexes are ordered, as I said. So what you can do is you can probably create another index, which is only on the column B. Because what if a query comes starting with B, only on the B, sorry. Then your index AB can't handle it because it's not the first column in the index. So you get rid of the index 2, but you create an index 3, which is only B. There's another not so commonly known pattern, which is what if you have the same index columns, but the included columns, which is what is called covered index. The part of the covered index is the columns are different. What do? You get rid of everything. And you add another index, which is amalgamation of both the columns in, covered index. So you add CDE as part of the included index, and that saves you a lot of space. You don't need a lot of indexes. You just need one carefully designed index. Right? 1 second. Second. Sorry, there was some my laptop got stuck. Is it visible? Sorry.
No, I think you'll need to share the screen again.
Reshare once.
Also, Lokesh, time check. We're about 5 minutes left into your talk.
Cool. Cool. Is it visible now?
Yes, visible.
Cool.
Go for it.
Cool. I'll just cover all the rest of the tips. So I think one fancy feature that SQL Server offers is the query store. It stores all the queries and the runtime stats along with those queries into a store that is asynchronously written. Now, what the power that it gives you is that you can effectively hunt for bad queries by looking at the store. So we built a handy tool on top of it, which is we call it SQL Police internally. It's sort of like a police that hunts for the bad queries. So you look at your compute utilization graph and see there's a spike. Then you look at which segment of the time frame has the spike, and then you look at the queries that were fired in that duration. Then you look at the query plans of those queries, and what you do, you then optimize those queries because those queries seem fishy. There are advanced ways of optimizing queries like forcing execution plan, or there are a bunch of ways. But yeah, you can figure out what works best for you basis the symptom of the query. Very obvious tip: archiving the data. Letting the database grow indefinitely is a recipe for disaster. Often as we treat our database as a data warehouse. We keep the data indefinitely, right? But sometimes we don't. We have to push it out to a OLAP store. What do you archive? You archive things which you don't need and which are steady or not changing over time. Yeah, that is what we ended up doing, and we saved a lot of money because if you transfer your data to a store which is cheaper, yeah, then your OLTP database is very efficient. One of the interesting tools that we built was SQL Police Slackbot. So I talked about SQL Police now, but there is sometimes you need a change which can propagate org-wide. So developers usually don't have time to look at the database, right? So what we did was we compiled a weekly SQL report that goes into the database, summarizes everything from what was my peak CPU, what my lowest CPU, is my database underutilized or overutilized using certain algorithms that we have. Does it have fragmentation, redundancy? Just summarizes everything to a PDF and sends it to individual owners. So now the owners are looking at the PDF and saying, oh shit, I need to optimize these things. And yeah, those, this is sort of like a org-wide change that we did to make sure that everyone is aware about how the database is doing. We built a tool called Snorkel that we ended up open sourcing. Aim was to make sure that database optimization and diagnosis is not only for DBAs, but for every single developers. And you don't need to remember any DMV to access this. So this is a simple architecture of how this tool works. But essentially, it's a collection of framework and metrics. So anything that your database to answer, for example, what are the active queries, what are the blocking queries, what is my fragmentation looking like, redundancy looking like, you can just use this tool and this tool will answer everything for you. So you don't have to be a DBA, you can be an engineer. And coming back to the same point, bridging the gap between engineers and people who understand databases. Yeah, this is one of the other tools that we built, DB Insights. Idea is that instead of looking at the database individually, we can just have a UI that populates every database in a single screen. It tells you with labels, like your resources overutilized. And that brings in the right accountability. And you can just click on it, downscale the database if it's overutilized, over provisioned. If it's underutilized, you know what to do. Yeah, this is something that we built. The key message that I have is like, you can always make things more efficient. Only if you understand the right trade-offs. And that usually happens when you place the context in hands of person who has everything in place to make the right decisions, right? Having the business context, the technical context, and that is possible when you invest in the right tools, you build the right tools. So yeah, that's all. I'll just have a couple of people to thank to make this all possible. So I have my team, Snorkel team, who built all the tools that I talked about. Lakshmi, Prakul, me. We put a lot of time into figuring out what the user problems were and building tools accordingly, saving our time in the end, so that we do fancier things than looking at databases individually. Special thanks to Kaushik, who pushed a lot for saving our cost and appreciating the tool, giving us feedback. Lakhani, who's like expert at databases, helped us a lot in figuring out a lot of gotchas. Swanan and Anand, who gave feedback for the slides and how to structure it. Thanks a lot. There are references in future learning reading that you can probably take a look. I'll be sharing the slides, so you don't have to copy it right now. Yeah, big thank you to everyone. I have my Twitter, LinkedIn, and blog and slides mentioned on this screen. You can scan this QR to go to the slide link. Okay.
Great. Awesome. Thanks, Lokesh. That's pretty insightful. Sarika, do you have any thoughts, inputs, anything that you'd like to share? Perhaps a war story of your own?
Yeah, definitely, Swanan. Thanks a lot, Lokesh. It was really insightful. And as I was sort of going through this talk, I was wondering, while it is so focused on SQL, there have been times when I have used or seen the exact same problems, even in non-SQL kind of DBs, not just in like RDBMS, but a lot of these learnings apply across the board, right? For example, when you say high latencies, it's such a relative term, right? Sometimes we see that something like an in-memory is so much better than putting your data on the disk, while if you have your DB on disk is much cheaper. The difference when I've seen like in past some use cases, the difference is between 1 ms to 5 ms, and it doesn't really matter because your application itself is taking like a second, right?
Exactly.
So it's extremely relative. So that was very interesting for me. Another thing you mentioned is 100 plus DBs across your different environments. One thing that I would say, and it has sort of bitten me in the past, is we focus a lot on our prod DB cost because the dev environment and the QA and other environment DBs are so small, and you typically pick up, the smallest instance. But when we started looking at it in one of my previous teams, we had 50 such instances, and even though the cost was small, just putting them all together on a single instance or just a couple of instances saved us like in our day-to-day costs so much without really doing any changes. So very interesting takeaways. Hats off to your Slack integration. I put it on the chat also. I think sometimes that is the difference between building the best tool and having the impact of that tool. So that's like taking it to the next step and making sure that there is actually an impact that you see. That was amazing. So hats off to you.
Thanks a lot, Sarika.
Great, cool. I think that brings us to end of part 1. Now, next up is Rohit. Rohit, in his own words, also a software engineer at Udaan, and he's going to talk about a lot more on and go deeper into SQL. But he's worked and a lot of his experience again directly on infrastructure and distributed systems. And while Lokesh spoke a lot on SQL, Rohit is going to speak a lot about NoSQL, right? So Sarika, one of your suggestions, taking it right up, and over to you, Rohit.
Thanks, Anand. Right. Okay. So good evening, guys, and thank you for joining. So I would be covering mostly our cost optimization journey for the NoSQL database. And for that, we choose Cosmos, but I think the concept will be generalized. And I hope that the learning that we gained would also help you at your org. So let me start. A couple of words. I am a software engineer at Udaan, and I work in infra and core team there. I mostly take care of the NoSQL database, and for which we chose Cosmos. Over the last 2 years, what we have actually done is that we strive towards reducing our infra cost, like majority of the companies that are doing right now. So we went down to the root level of optimization for the database fine tuning and explored multiple experimentation feature also, and figure out what's the right fit for us. And in the due process, we ended up reducing 75% of total cost. Another benefit that we got was that while we fixing queries, the performance got boosted and our DB latencies decreased for the services. So that was an cherry on topic. Okay. So when we started, we chose Cosmos DB as NoSQL. So it was very easy to scale up and scale down at real time also. So at for sales event, the business team need not worry about whether my DB will scale or not. He can simply scale up or scale down depending on the use case, and he can focus on the business logic. Pricing model were quite dynamic and flexible for the different type of use cases. So that was another win for us. Like we had like availability guarantees and low like read-write latencies. I think like today most of the cloud provide. So that was also one of our requirements. And another significant factor was that there's no virtual capping on the storage and compute. So you can we store terabyte and terabyte of data in fewer of our collections without any issues. But again, you have to keep that in mind. It comes at a cost. And that brings us. So as the scale grew, there was a subsequent impact on the cost. It was a non-linear growth of the cost. And then we started figuring out what can we do to fix our database like issues. So our journey starts from here. To see that we're truly scalable, we must ensure that our like total cost should be proportional to cost. Like it should be direct linear relationship. For example, if I say our total cost is roughly total queries into average cost per query, in this case, average cost per query should remain constant. I mean, it should not increase over time or with like with the data growth. So most of the time, what happens as the data grows, average query per like average cost per query also increases. So in the two diagram, if you see, if the average query per average cost per query remains constant, your total cost will remain in check. But even the slightest of the delta in the like cost per query is there, your cost like exponentially increases. So this is the part where you need to keep focus on throughout the journey if you are able to maintain this linear. Okay. So before I proceed, there are a few terms that might be specific to Cosmos, but I want to make this generic, so I will cover it. So one other term I would use is RU, that is request units. So it simply says like in database world, what is the total expense of your query? So it comprises of your memory charge, CPU charge, IOPS charge from your databases. It is very similar to RCU, that is read compute unit and write compute unit in the AWS world. Next is the provision throughput. So it signifies how much resource are you actually provisioning for your DBR collection. An example would be, I can say I have provisioned 10,000 request unit per second capacity for this. And last term would be utilization percentage. And we do keep a watch on this. If you are provisioning something, of what percentage of that are you actually using? So are you over provisioned, under provisioned? You must keep a watch. So our journey started understanding what our business use cases was and how does the traffic looks like during the day. So in majority of the cases across any org, you will find the traffic pattern will fluctuate. Cron jobs can especially make the traffic spiky. So in that regard, for example, in this regard, we mostly have a cron job and rest of the day traffic is pretty low. So if we go with fixed provisioning, like we provision like for the max throughput, we would have ended up wasting like 90% of the resource majority of the time. And it was quite an overhead. In this case, like we are hardly utilizing 10 to 20% on an average throughout the day. So we're losing a lot in this. So we use for auto scale model, and similarly, like in the Azure world, in AWS world also, there is similar pricing models. So we went with that, and the thumb rule is that you pay for what you use. Minimum 10% will be charged, but you pay for proportionate to your usage. Now, in this case, when the spikes are not there, we only end up paying 10%. So that is 90% saving in the non-peak hour. So overall cost we saved roughly was 60 to 70% here, just due to change of a pricing model. There is a catch here. So autoscale model, in the base price of autoscale model, it's 1.5 times higher than the manual and fixed throughput model. What does that mean for us? So I will take an example. For example, you have provisioned 10,000 request unit per second. So for example, in your manual or fixed mode, you have a provision like $500 per month. That's the pricing model. Then the autoscale model will charge you $750 max because it's 1.5 time multiplier. And depending on your traffic, you would end up paying $75 to $750, depending at 10 to 100% usage. As you can see, after a given point of time, autoscale actually becomes expensive. So autoscale is not this one-shot solution to all your problem. Be careful of that. Understand your traffic pattern. To be precise, this number is 66%. Like we have done our analysis, we have built a recommendation tool on top of it for each services. We do the mathematics, what is the best recommendation for them. And after 66.6%, go for the manual mode. That will make more sense. For example, in this use case, average utilization is 85%. So here manual mode or fixed throughput mode saved more cost for us. Okay, at Udaan, like we have terabytes and terabytes of data and they keep on growing with time. We have to be careful, like the cost should not increase as the data grows, like at least the scale part should not grow with that. So what Cosmos DB or in fact any NoSQL DB would do here is that they will keep adding physical machines on top of it, and your queries will get, data will get distributed across these machines. So these are physical machines. As your data keeps growing, your DB will keep adding these machines like to handle the load. But it's not as smooth as it shows. There are like some caution you must keep in mind here. So a key concept I would like to emphasize here is that logical partition versus physical partition. So logical partition is the partition key that you define for a service. So suppose I can choose my city column is my partition key, right? So it can be like that. And the physical partition is the physical machine where this logical partition resides on. So as you can see from diagram, our logical partition key was city, and all the logical partition get distributed across the physical partition. So remember in mind, like you cannot choose which logical partition ends up where. It will be like hashed automatically. And one logical partition will only reside in one physical machine. So that's why partitioning is actually quite effective. So what does this mean for the cost impact? As you can see from diagram, if I have employee container, right? And if I, let's say query, okay, give me all the employees whose city is Pune and age is greater than 25, right? So it knows exactly which physical, you have told like my city is Pune, it knows exactly which physical partition to hit, and it will only query from that machine. It will be faster, it will be cheaper because you compute only on one machine. Now, in second example, if we say, okay, give me all the employees whose division is IT, let's say, and age greater than 25. In this case, you could not pass, like did not have the knowledge, let's say, of the city, and you cannot pass the partition key. So what the database will do is that it will query, it will pass on the query from each of those machines. It will query all the 5 machines and then aggregate the result back. So you will incur compute cost on all the 5 machines, as well as the latency will also be higher. So that's the cost of cross-partition queries. And we found out like these were real pinpoint for us. Okay, another key factor is that, let's say as your data grows, your number of physical partition will increase. Let's say today it's 5, tomorrow it's 20. So now your cross-partition query will hit 20 physical partition. So each query itself is becoming more expensive. So this breaks the cost linearity graph, and we have to keep this in check. So how did we fix it actually? So first of all, telemetry and monitoring is a developer's best tool. So we added a flag for this internally based on the Azure diagnostics. So almost all like cloud provider will provide you diagnostics. So based on that, we figured out is this query cross-partition, and then we decided what cost, how much RU cost is it incurring for us, and where to focus on. And then we found out, okay, these are the weak areas, these are the queries that are incurring us too much cost, and these are the container and queries we have to optimize. So we have to choose a physical partition, logical partition very wisely. You have to see what are the queries that you like in your queries, what are the columns that occur the most, which are static. You cannot change the partition key, of course. So let's say status cannot be a partition key because it can change like dynamically. So keep in mind. Also, another point, once you have made your database, in real time, you cannot change the column also, which like if you have made on city in the real time, you cannot change it to division. you have to migrate the database. You have to create a new database and migrate. So it's a real pain for it, especially in prod. So think ahead of time. This will come to bite back if you choose it carelessly. Okay, now there can be use cases, let's say for us, one is based on, let's say, city, and one is based on division, and both are valid use case for you. So in second case, division has to go cross partition. There's nothing you can do about it. So there was a feature that we experimented and it works really well. It's called materialized view. And I hope like majority of you folks can gain benefit from it. What it does is that the concept is pretty simple. You create a copy of the container in the background. So let's say my original DB was partitioned on city. It will create a copy based whose partition will be on, let's say, division. And the view materialized view builder based on the change feed will keep these two in sync. Right. So second copy will only be read only. All your reads and general reads and all the writes will go through the original one, and it will update this secondary DB accordingly. How does this help you? Now, for example, I'll take in the last query you saw our total RU cost was 259 here. On the same query, had we used the queries that have partition key, we end up paying 15 to 20 RUs. So it's like more than 10x saving. So if you choose there will be duplication cost. So your write cost will double. So make sure your writes are not more than 30% of total operation. Otherwise, it may backfire. Otherwise, you can save up to 10x upon your this cross partition queries, and that can be a big save. Overall, we ended up saving more than 40% on an average for this use cases. Okay. Also, on top of that, channel topping, your queries will also be faster because it only pings one machine. So a reduction in latency is an added bonus on top of it. Okay. Next, we observed here is that even for the queries which were partitioned, even then the cost of query was pretty high and the cost was increasing. When we narrowed down what the root cause was, that it was hot partition. And trust me, it is one of the most difficult problem we had to face. So what a cross partition basically means is that if a particular partition is significantly more active or more used than the remaining partitions. For example, in this diagram, your partition number 3 is the hot partition. So how does hot partition cause an issue? So let me take an example. For example, I have provisioned 5,000 RU per second for this container. And the let's say service owner thought, okay, this is sufficient for my traffic. So let's say I have 5 physical partitions within it, and the DB will distribute this 5,000 RU equally among them. So each of them will get a maximum 1,000 RU. Depending on the auto scale, it can go between 100,000 RU. Now, as you can see from example, majority of the physical partitions sitting idle while the hot partition is choking. So even though you have sufficient resources at the container level, but that individual partition will start throwing 429, it will get throttled. It can cause a bottleneck. So even you can think even though I have sufficient resource, why I'm getting throttled at 429? It's because of this hot partition issue. So it's a major performance bottleneck also. Second, coming to the cost impact. So the current pricing model of Azure dictates that we will end up paying based on what is the maximum across all these physical partitions. For example, partition number 3 is 90%. So we'll end up paying 90% for all 5 of them. Had we if I take it a one step further, as the data grows, let's say you have 20 partition now, you would have ended up paying 90% for all 20 of them. So this again makes the cost non-linear and really painful to tackle with. Now fixing it. Unfortunately, fixing hot partition is not that straightforward. The best you can do is that detect there's a hot partition and find out what logical partition is making it hot, increasing the traffic. Even after you narrow down what logical partition, from a technical standpoint, there's no easy fix for this. The business has to analyze whether the choice of a partition was right or whether they have to redistribute or rehash the partition. It's up to them. But again, this is a major step and it's not a quick one-stop fix. For our use case, we use log analytics offered by Azure. So internally, what it does is that it gives us insight. What logical partition key is count of what logical partition key is how much in each physical partition. So for example, from the graph, we can see the top 5 234, 152. Those are the ones that were actually making this hot. They were this is only the top of the table. There were many more below, but we found the main culprits that were making out these physical partition it's more expensive. again, fix will again come from the business side, and the service owner has to understand this. The best you can do is that detect the hot partition and narrow down like what is actually making it this way. Okay. Next part is that we also explored with our share with indexes and composite indexes. Okay, so by default, Cosmos indexes all your fields and nested fields. It's a document like it's a JSON structure, so it also indexes all the nested field also. Practically speaking, we only require hardly handful of them. So indexing on all of them can be like 20% overhead in the writes. So in this case, we went down and find out like what are the queries, what are the fields we query upon most often. And we only chose the query of fields which had high cardinality. Okay, so high cardinality means the variation of the data type should be very high enough. For example, if you do status can only be 5 to 10 types, success, like pending and all those. It will give you very less bifurcation, but it will create you overhead of the writes. Writes will become expensive of this. So if you're choosing index, make sure you make it count. Choose it with high cardinality and the ones you query upon often. Okay, next was the composite index, and it saved us a lot, especially where we had multiple where clauses and especially where the order had to be maintained. You can have multiple ordering by on multiple field. Let's say status, you can have ordering by like last updated as well as creation time. Let me give an example on this. This was one of our query. It had roughly 6 fields to filter upon. So only indexing was there currently, and the cost we incurred was something like 3,000 to 5,000 request units for this, which was quite heavy for like one single query. So we added composite index on top of it for the first 5 fields, and the result were quite marvelous. Simply adding composite index brought down the cost to 130 to 150 RUs. So in general, most of the use cases, indexes help a lot, but composite index, I have found like people generally miss out in the NoSQL world. Okay, but there was few catch here. There was a lesson I learned the hard way. For Cosmos, in Cosmos, the fields in which your query occur in field, like in the order of your fields in the query matter a lot. For example, in this, if I have this composite index, if I pass assign to after or before descriptor, if I change the order in the query, the composite index will not be used, and neither will there be any alert from the Azure side. This is something you have to take care yourself. So we have built our built the tool. Actually, this is actually work in progress. In fact, that can tell us if there is some optimization here, because it's a silly mistake at a huge cost. You can save 95% of the cost simply by using partition key, but if you mess the order in the query, it will backfire. So just remember, the order of the fields in the query is sensitive to composite index. Okay, now as Sarika said, we also face this issue for our dev resources, especially. In some of the use cases, we saw that our traffic pattern is very low. Only 100 RU per second would have sufficed. But if we start dedicating like minimum resources, 100 RU per second to all of them, we might have like 50 to 100 dev resources. If you allot to each one of them, there will be huge wastage. So what shared throughput gives us is that we can provision a small amount of resource and we can share across multiple container collection. For example, for our dev resources only, we have used up to 25 containers at cost of only 100 RU per second, and we ended up only paying $8 to $10 a month. So that is pretty cheap, and especially it can save a lot on a dev. Even we came to the similar conclusion that dev also became expensive after a given point of time. It was simply being ignored, but when we came back to the findings, we fixed this actually. Okay, analytical storage. This is actually quite interesting. As you can see, a lot of our use case was based on cron jobs, and cron jobs behave like most of the time it will be idle, but when it comes, there will be huge traffic. They will do operations in bulk. So analytical storage it's a background copy of your actual main DB. It's free of cost, and auto-sync roughly takes 1 or 2 minutes at max. So that's the latency they have. The advantage you get from this extra copy of the data is that you can read from this directly. You don't even need to hit your main DB to bulk for the bulk ingestion of data. So now reading from analytical storage is very cheap. I think it's somewhere around 1 lakh read can cost you like 5 to 10 cents or something like that. It's very cheap. So now you can ingest data from your for your use case at 1/10 the DB reads cost. So this was one of the win. Extending it further, you don't even need to provision for cron jobs, because cron jobs can be quite unpredictable. You have to understand and provision just to scale higher. Because of that, that goes away now. You leave the task, you read from analytical storage in the cron jobs, and your DB is only for your transactional purpose. One caution here is that you cannot update via analytical store. So in case you have a bulk job, a cron job that updates the data, then it won't work for you. Then you have to go back to your main DB store. How did we actually make it work? So for example, in this cron job, even with auto scale, minimum we are paying with 10%. So if you can see, there's still significant loss of RUs. Now, in this use case, if I remove the cron job, then we were actually hardly utilizing 5% of it, right? So once we migrate to the analytical store, we can now scale down to like whatever was the 5% of the original one. So even in the auto scale model, it gave us a further 60% saving. So from total, if you used provision like manual mode, you would end up saving 95% of your cost. So this was another win for us just by using analytical storage. So we need to make sure we are using we are leveraging the right offerings by whatever cloud service provider we have. Okay.
Yeah, Rohit, time check. We're about 5 minutes left of the original allotted time.
Yeah, that should be sufficient. Okay. Now, since in majority of the cases we used auto scale, and auto scale prices can be dynamic. It depends on the scale, whatever utilization you have. So if suddenly something goes wrong, you would end up paying more. Predictability of data is less here. In fixed model, you know what you're built for, but in auto scale model, prices can go unpredictable. So we need proper monitoring levers as to if our prices are suddenly spiking up. So two main parameters I would recommend, like it worked for us, is that average cost per query. If there's any change in that, go back and figure out if there is hot partition, cross partition, indexing issue. So fix that immediately. If you can see here is that the given graph shows average cost per query. It suddenly spiked for us. We figured out how to what was the issue, how to fix it. And after a given point of time, it went away. So we need to keep this in check. Second thing is that we also monitor total request and total request unit spikes. What this actually means is that if your total request is spiking without any increase in organic business traffic, that means you have some unoptimization in your workflow. Maybe a failing cron job is bombarding your database again and again. So you need to even keep that in check. So we also have alert on top of that. And finally, so over this journey, we had our own share of learning and experimentation. But an important part of this is how do we apply it and use it across the board. So like Lokesh said, the service owner might not have depth knowledge of a database, and neither they can have the bandwidth of that. So we built an internal tool on top of it. We ingested the service real-time traffic for spike detection. We also ingested the usage pattern to recommend, okay, whether manual will make more sense to you, autoscale will make more sense to you, or whether you're under provisioned, over provisioned. And then we also take into account the query performance stats, whether you are using cross partition quite often, or whether you are missing some indexes, your index lookup time is high, or your latency itself is high. We further club it with the historical data, because we have seen sometimes there can be pattern, like few days of the month, the traffic itself can grow, like end of the month, maybe your traffic is higher. So we also account for the historical data, and then we find out if there's abnormality in your traffic pattern or usage pattern. Then we set up the alert rule, and it simply generates very readable alerts and recommendation for the team, which now service owner can simply apply. It can be like, okay, switch to auto scale model or scale down to this much RUs. Or it can be like add a composite index, your index lookup time is higher. So majority of the time, it will be very easy to fix, and you can apply your learning throughout the board very effectively. Yeah, thank you guys. I hope you enjoyed.
Great. I think there's a question. Can tools like Datadog help in some cases that Rohit mentioned? It's a question from Rajni.
Frankly speaking, I've not used Datadog, but what I can see is that integration part and how you analyze the data, of course, I think Datadog is your analysis tool, right? I've not used it personally myself. So we have, if you can find the pattern, right, for our use case, Yes, it might have helped given we have sufficient historical data, then we could have proven it. It simply depends on your use case. Yes. You have the data, you have to analyze it. Just make sure you keep the data, you also maintain the compliance. You cannot send the data outside your org. If till then, I think any tool is good. You simply need to understand what are the thumb rule, like when auto scale makes more sense, or when manual makes more sense, or cross partition query, how to fix that. You need to just remember this lever. You can use whatever tool you want.
Hey, Rajni, does that answer your question? If not, feel free to unmute and,
We can have a
go.
discussion.
Yeah.
Okay.
Okay, cool. Great. Going back to Sarika, any thoughts, any comments, suggestions?
Hey, definitely. Thank you so much, Rohit. That was really insightful, especially when you talked about this analytical store. This I wasn't aware of. I haven't worked with Cosmos DB personally, but other DBs also. Now I'm curious to know which all DBs sort of provide this, because this definitely can be a game changer when it comes to these patterns, right? Where you typically have a very low volume of the user path queries or the writes happening, but there is a very high volume of the cron jobs read.
Yes.
So something I'm very curious now to find out what all sort of tools or what all DBs provide this analytical store. Could definitely be a game changer in terms of cost. I am also very, very impressed by both of you, how you've contextualized all the optimization levers we talked about, right? Because it's like in the real life, it's always a trade-off between your use case, what you want, and how it changes. And the way you've contextualized it, when it works, when it doesn't work, the decision framework is amazing. So thank you both for that. A couple more things I want to sort of just touch upon. I want to double click on the average query cost that you mentioned. I think it's really, really important. And most of the times we don't do that. We don't track how it is moving. We don't look at how it is moving across time. And it's very easy for us as engineers to say that the cost is increasing because the requests are increasing without really looking at whether it's linearly increasing or it's exponentially increasing, right? So that's a very important tip. And I do want to double click and make sure that that's like one of the key takeaways everybody takes home. Yeah, another thing, when you started talking about partitions, I was so excited. I wanted to hear more about hot partitions. And when you said it's a tough technical problem, I was sort of heartbroken. So let me just add a couple of things that I have seen in the past when it comes to hot partitions, right? I'll take just a couple of minutes, Swanam, if that's okay. So when it comes to hot partitions, there can be different reasons why it happens, right? One reason could be you have a handful of hotkeys. If you think about, let's say, an e-commerce engine, there is an iPhone that's selling at the deepest discount. So everybody is going to search for that. And that means you have maybe a handful of keys which are hot. So one way you could look at that is you could identify which queries are your top queries or which keys are your hot keys, and then have in your application a layer that essentially duplicates those queries. So instead of keeping one record, I could keep 10 records for such queries. And then I could randomly pick one of them when I'm reading, whereas when I'm writing, I write them consistently. That is one. Another thing that I've seen in the past is a pathological case, wherein you have your user data set and you have this one or two user accounts that you will see are extremely different in terms of data size, in terms of accesses. When we dig into them deeper, we identified those were those default keys or the test users. So those are the pathological use cases that you should always look for when you have the hotkey issue. Besides this, definitely you can also have a hot partition issue when it's not just one key, but it's the key that you partitioned on, because the data size is different, right? When you give the example, Pune versus Bangalore, your users in Pune, of course, might be lesser as compared to your users in Bangalore, and hence you get into those situations. There, one thing that I've seen in the past that worked was having a composite key. So while you have the city, for certain cities, you do a composite key where beside the city, you also put a sub-region or a region, collection of pin codes, that kind of a second level of partition that helps you distribute the load of that particular partition into multiple ones. So just some tips. But thank you so much. Extremely wonderful talks from both of you. Really, really insightful.
Right. Actually, composite index we used, but for the time's sake, I did not include that in the slide.
Okay.
So composite index also, so there are two factors. Is it hot because of throughput or because of the storage size? There are two factors.
Yeah.
So sometimes adding a timestamp to the composite index key can help. As the data size grows, your each physical machine also has a limit. For example, 20 GB limit. If you exceed that, nothing can save you. So there you have to add time-based logic also to redistribute your data. And second fix was that we use this actually, but I would have to go in depth to discuss that. So caching. So caching can help. Write through cache can help for your hot partition keys. But we have seen that some cases updates themselves are hot. In that case, caching will also not save you. So those also were some hard lessons we learned there. So hot partition is one of the worst problem to have.
Definitely. It's a problem that kills you, especially when it comes to the cost, right? Because it just changes everything in terms of your overall data versus that one partition. Yeah.
Correct. I think a lot of cost optimizations are built on predictability and patterns, and hot partitions usually break those patterns and they go out of the predictability zone. And it's really hard to account for that in advance always. The other theme I want to add here, because somebody I think Rajni mentioned Datadog, is anomaly detection, which is a new style of optimizations that New Relic and Datadog also help quite a bit. Is they have your metrics and roll-up tables, all your logs in one place, and they're constantly running these models. And the moment something that looks out of the ordinary from your usual pattern, they flag it for you. Like for example, in our case, we get a traffic spike in the morning every day, predictably, right? So when the traffic spikes in the morning, it does not alert us because we already know it's going to happen. But if it does spike in, let's say, the afternoon or starts increasing, it alerts the on-call team. And so a lot of the anomaly detections, when we ran it over time, we saw that there were patterns, even the anomalous patterns were patterns that we previously missed. And then we were able to optimize further by changing container sizes, etc. And so this is something that classically cost optimization techniques missed out on, but tools like Datadog and New Relic are helping with. Again, like something of an add-on for everyone. And then Rohit, I had one question for you. The query gotcha that you mentioned about ordering being important in a query, that sounds very awkward to me. It's something the database should fix. Did you take it up with Cosmos?
Yeah, I took up with them multiple times.
Okay.
So they said that for internal optimization, that's how it is designed.
Okay.
Actually, so the PM who communicates with me from outside, he said he will set up a meeting with me from the folk who designed this indexing. So
Understood.
I also want to understand the philosophy behind this. So that is, they said it was because of faster performance. Otherwise, I do not know which tree they use. They said they are using a modified B tree version. They built it on their own. So even I want to understand that. I'm asking for a meeting with them.
Got it. Because for example, MySQL and Postgres Query Planner does this exact thing, right? It takes away these silly mistakes. So as long as your index ordering is correct, I think, which everybody knows that your order and index is important. If order and query start becoming important, then it's a pretty downward spiral of bugs coming one after the other.
They won't be alert also. We learned this very hard way, actually.
Yeah, makes sense. That's actually pretty good. Like, I would not expect that, right? This is completely counterintuitive. So nice.
Yeah,
great. I think that brings us to the end. Does anyone have anything else? Anand?
I just want to add one small thing. Sorry, I'm kind of in a dark place. It kind of reminds me of the performance optimizations kind of used to do long back, right? I think there's this adrenaline rush kind of you kind of spotted something new and then that saved you 10% of time, and it's kind of very interesting thing to kind of go through, right? I mean, how was it like the joy of kind of finding these things?
I think your last few seconds got cut off, Anand.
No, I was just saying that there's a lot of adrenaline rush in kind of finding this new hotspots and kind of trying to optimize that. And I think that's kind of must have been a very interesting experience.
Yeah. In fact, as new offerings come, we have new levers to leverage. For example, Antica storage, it came and we leveraged that. So we have to keep an eye out like what's there in the market right now.
Very interesting.
Cool. Great. I think that brings us to the end of today's session. Lokesh, Rohit, thanks for sharing and also condensing, 2 years worth of work into like a tight 1 hour narrative. It's not easy, but I think both of you did a pretty good job. I enjoyed it. So I think there are a bunch of amazing comments from Sarika as well. I think we should do the job of like summarizing and putting it on the Hasgeek page, so that whoever is watching it in the future can come back and refer to it. And we'll share, I think slide links have been dropped in the chat, but we'll share them on hasgeek.com as well. If you're subscribed, you'll get a notification with the update along with the notes from today. So that's it for today, and we'll see you at the next event.
Sure. Thanks a lot, everyone. Hasgeek, Swanan, Anand, for organizing this.
Bye, everyone.
Bye, guys.
Bye, everyone.